Hello, my name is Vitali, and I would like to present our tool for visualizing verification results. Software verification ensures that a program meets its formal specification. Static verification tools can prove correctness or report potential bugs. However, interpreting their results is often a manual, complex, and time-consuming task. Our tool addresses this challenge by presenting those results in a more accessible and human-readable way. This is the main overview page, providing a high-level summary of the results, using Linux kernel modules as an example. It shows how many modules were verified as safe, how many contain violations, unsafe, and how many remain unknown, typically due to timeouts or tool failures. The unsafe results are usually the most important, as they indicate potential bugs that require further investigation. On the unsafes page, users can browse entries with detailed information about potential bugs. The list can be sorted or filtered, for example, to display all error traces related to a specific module. Let's look at an error trace found in a Linux kernel module during verification of clock API usage. In this case, we're checking that every call to disable the clock is properly preceded by a corresponding call to enable it. And here is the error trace itself. The interface is split into two panes, an error trace showing a step-by-step execution path from program entry point to the property violation, and the source code. To support manual analysis, our tool offers several key features. Firstly, critical operations that are most likely related to the bug are automatically highlighted. These so-called violation hints are taken either from the verifier itself or from the property. Secondly, the trace is displayed as a collapsible call tree. By default, only the branches containing violation hints are expanded, highlighting the most relevant parts of the trace. However, the users can manually expand any branch to explore additional details. Thirdly, each trace step links directly to its corresponding location in the source code, significantly speeding up the analysis process. Fourthly, low-level details, such as assumptions and declarations, are hidden by default to significantly reduce the size and complexity of the trace. Users can easily switch between the full and simplified views. In this particular trace, we see that after enabling this clock, the potential error path was not handled. We identified this error trace as a real bug and added a description. To do that, we simply marked the trace by filling in the relevant fields, so if it appears again in future runs, it will be automatically recognized. This particular issue was later reported and fixed in the mainline Linux kernel, as confirmed by the corresponding commit. Now, let's look at another error trace, this time related to memory safety. In this case, the probe call may return null, which is stored. Later, during cleanup, that same value is retrieved and dereferenced, leading to a possible null pointer dereference. This trace highlights the value of our violation hints, showing exactly where the variable received the null value and how it was passed to the point of dereference. Our visualizer also supports regression verification by comparing results across versions and marking previously analyzed error traces. In this example, all traces were already known, so no new manual analysis is needed. However, in cases where there are over 600 new error traces, manual analysis becomes more complicated. To address this, we can switch to the comparison view, which highlights only newly introduced bugs, those most likely related to recent code changes. As shown here, only 35 traces are new and should therefore be prioritized for the analysis during the regression verification. Our tool supports any svcomp verifier and can visualize results in standalone mode. Simply provide the witness file you want to analyze, along with the corresponding source code, and an HTML page with the visualization will be generated. Here is the resulting visualization. Note that it can be used independently of the full results interface. Additionally, Witness Visualizer offers automated feedback for verifier developers by identifying missing witness elements, which may help to improve visualization. You can find more information about our tool in the GitHub repository, along with additional examples in the artifact. Thank you.